So far we have looked at what is the effect of hydrophobicity on activity. So, when we have a series of compounds where we systematically vary the hydrophobicity by measuring what is known as log P, we can study the effect of activity on log P. Okay. So, we looked at the possibilities of even varying a substituent on a benzene ring or an aliphatic ring, and what the effect of a single substituent is on the hydrophobicity of the molecule. So, we looked at P, we looked at pi. Okay. Now, hydrophobicity is one of the important characteristics of a molecule. So, today or now we look at what are the other effects that can come into play. So, the first effect is an electronic effect. Okay. So, as you know, molecules have an electron cloud around it, and these electronic effects can play a major role in binding, especially in non-covalent interactions. Now, one of the important electronic effects is on ionization or polarity. Okay. So, one of the standard ways of looking at ionization is to look at acid base equilibria. Okay. So, if I take benzoic acid and dissolve it in water, I can determine what is the ratio of benzoate to benzoic acid. So, benzoic acid equilibrates in water to produce benzoate and H3O plus. Okay. Now, we can take benzoic acid and put it in water and measure the amount of benzoate that is produced, and from that we can determine a equilibrium constant. Keq is nothing but the concentration of benzoate COO minus times H3O plus divided by concentration of benzoic acid times water. Okay. This equilibrium constant will help us understand how the benzoic acid partitions into the corresponding conjugate base. Right. We already know that this is a measure of acidity. The higher the equilibrium constant, that is greater the Keq, the better the acid. Okay. So, we already know this, right, and the acidity of a molecule is determined by the stability of the conjugate base. So, the stability of this conjugate base here is going to determine the position of the equilibrium. Now, the stability of the conjugate base is determined by how delocalized the charge is. The more delocalized the charge, the more stable the molecule is. So, by putting an electron withdrawing group EWG, EWG is electron withdrawing group. Okay. What happens is that we pull the electrons from the carboxylate and help it get delocalized, and the more delocalized it is, the more stable it is. Right. So, by putting an electron withdrawing group, I am going to push this equilibrium towards the right, and therefore, the acidity improves. Right. Conversely, if I have an electron donating group, that increases the localization of the charge on the carboxylate, and therefore, the K equilibrium is going to go down. So, therefore, in order to study the effect of an electron withdrawing or an electron donating group, I can use benzoic acid benzoate equilibrium as a model system. Now, we already are familiar with how a particular substituent can have an influence, whether it is on the para position or the meta position. So, here is an example of a nitro group on a benzene ring. So, if I draw out the resonance forms, I see that there is a charge being localized in the ortho position and the para position, and whereas the meta position, the charge localization is not very good. Right. So, therefore, there is a differential in the way in which electron cloud is going to distribute itself in this particular case. Now, similarly, when I have a substituent nitro group in the meta position, the influence on the carboxylic acid is far lesser than when I have it in the para position. So, these are concepts that we have studied previously in our organic chemistry courses. So, I am not going to repeat these things at this point. Right. So, what Hammett did many years back was to introduce a term called as sigma, which is nothing but the Hammett constant. Okay. So, what Hammett did was he took this equilibrium of benzoic acid, which I am drawing out here, C double bond O, O H plus H2O, giving you an equilibrium with. So, he took this equilibrium, what we write as, let us say, K, okay, and this, by putting a substituent X on this, he defined a parameter known as log of Kx by Kh. This he called as sigma. Okay. So, if I have a substituent X that increases the equilibrium constant, which means that that becomes a better acid, which means that the conjugate base is more stable, then I would have a higher sigma value. Okay. Conversely, if we have a substituent which decreases the stability of the conjugate base, and as a consequence the log Kx by Kh would be lower, okay, and in this case it can be negative, right. So, therefore, sigma is a measure of how well the substituent influences the position of the equilibrium of benzoic acid and benzoate, okay, assuming that benzoic acid is the benchmark. Now, based on this, we can derive sigma values for various substituents. So, let us go through a few of them now for us to have a better understanding. So, keep in mind what we looked at was nitro group. So, nitro group basically can help stabilize the negative charge on benzoate much better, and therefore, the position of the equilibrium is going to favor the benzoate when compared with the corresponding benzoic acid. Okay. I will repeat this. So, when we compare the stability of the conjugate base with para-nitrobenzoic acid, which is para-nitrobenzoate, it is significantly more stable than benzoate. Therefore, the position of the equilibrium in the case of para-nitrobenzoic acid will be far more in favor of the conjugate base, and therefore, log of Kx by Kh is greater than 0, right. So, the value for 4-nitro is 0.78, and as you can see here, there are a bunch of electron withdrawing groups, and all these values are somewhere in the positive region. So, cyano is a very good electron withdrawing group, chloro, fluoro are by electronegativity, they are quite good at pulling electrons towards themselves. Now, let us look at the case of an electron donating group. So, if we have benzoate as I have drawn below and look at the conjugate base, the example we take is NMe2 and CH3, CH3. Now, this has a lone pair of electrons which can be pushed into the benzene ring and it destabilizes the conjugate base. Therefore, the position of the equilibrium in the case of N,N-dimethylaminobenzoic acid is going to be far more in favor of benzoic acid when compared with the parent benzoic acid. So, therefore, electron donating groups such as here are going to have a negative sigma value, because what we looked at earlier is log of Kx by Kh is going to be less than 0. And therefore, this gives us an estimate of how a particular substituent, in this case in the para position, influences the electronics of the benzoate or the carboxylate, and it helps us understand what is the influence on the level of ionization and also on the level of polarization, right. So, this parameter is very useful to study electronics. Now, this also works for a substituent in the meta position, but once we start putting substituents on the ortho position, sterics will come into play, and therefore, we do not consider ortho substituted benzoic acids in this analysis. We will look at in detail the effects of sterics in the later part of this course, right. So, the effect of the electronics can be studied using this Hammett scale. So, here is the equation that Hammett defined. So, if I take the K of a substituted acid, so K equilibrium can be converted to Ka by factoring in water. So, if I consider the Ka of a substituted acid and compare it with the Ka of benzoic acid, if I take a log of this, then we have already defined sigma as being the ratio of these two parameters, and now the slope in this case would be 1. So, if I take log of Kx by Kh for the case of benzoic acid and plot it versus sigma, then I would get a straight line with a slope of 1 and intercept of 0. Now, this is because we are comparing the values of benzoic acid with benzoic acid. But now, if I take a hypothetical reaction which let us say is ester hydrolysis, and if I measure the rate constant of hydrolysis, then I can determine Kx, which is basically the rate of the reaction with a substituted benzoyl ester with an unsubstituted benzoyl ester. So, here is the example that we are taking. So, we take these ethyl benzoates and react them with hydroxide ion at 30 degrees in ethanol and water. So, what we would expect would happen is OH minus attacks here, and then this goes back out and it generates a tetrahedral intermediate, which then can subsequently collapse and kick out ethoxide, which will give you AR C double bond O OH, which is going to rapidly equilibrate with AR C double bond O O minus. This is an example of a reaction that we want to study and how the reaction is affected by changing electronics. So, what I need to do is to determine the rate constants of the reaction and then study what happens when I change the substituent. Now, what we do is we take this log of Kx by Kh and then plot it versus sigma. So, this is how a typical Hammett plot would look like. Okay. So, keep in mind a positive sigma value means that it is in an electron withdrawing group, and a negative sigma value means that it is an electron donating group. So, when I plot this ester hydrolysis versus sigma, I get points such as this. So, each of these is a individual rate constant Kx divided by rate constant for H. Okay. So, if I take this point here, this is nothing but Kh divided by Kh, that is equal to 1, and the log of that value ends up being 0. Now, if you look at this plot, you can see that electron donating group has a slower reaction compared to hydrogen, whereas an electron withdrawing group has a faster reaction. Okay, that is the first observation we make. The second observation is you can actually fit it to a line in what we learned earlier, which is linear regression analysis, and then you can determine the slope, which is nothing but rho, okay, and you can also determine the linear regression coefficient, which is r square, which we have said that if it is greater than 0.8, then it is a good fit to a line. Okay. So, this study allows us to predictably study what happens when I change a substituent on the rate of a reaction. In this particular case, we have taken rate of ester hydrolysis. Right. Once I fit this into a line, let us say I want to accelerate the rate of reaction, I know that I have to look at higher sigma values. And if I want to slow down the reaction of ester hydrolysis, then I need to go to lower sigma values. Okay. And therefore, it is a predictable mechanism that one can use to design the next set of compounds if needed. Now, let us look at another example where we have a similar Hammett plot for another reaction where the trend is exactly the opposite. An electron withdrawing group which has high sigma value seems to slow down the reaction, while an electron donating group which has a negative sigma value makes the reaction go faster. Okay. So, now if I fit this to a straight line, I can get a linear regression coefficient r square. I can determine the slope, which is basically rho. Here in this case, rho would be negative. Okay. What this tells me is that in a particular series of reactions, the mechanism of the reaction involves a transition state that is sensitive to electronic effects. So, therefore, you can have a situation where the electron donating group can accelerate the reaction, whereas an electron withdrawing group can slow it down. We will not go into too much detail about Hammett plot. Now, let us look at a case study where we have looked at the insecticidal activity of these organophosphates. Okay. So, here what we have done is we have taken this phosphate and there is we have systematically changed the group on the benzene ring, and when I study the insecticidal activity, I get a QSAR equation of this sort, and it showed that the electronic effect had a tremendous influence on the inhibitory activity by this set of molecules. Okay. So, these molecules, we find that an electron withdrawing group on the aryl ring enhances the activity. So, an electron withdrawing group on this ring increases the activity, whereas an electron donating group slows it down. That is indicated by the slope K1. Okay. And K1 being a positive value means that the electron withdrawing group would increase the activity. These molecules were later found to be targets for acetylcholine esterases, which are expressed outside the membrane, and therefore, it is understandable that the organophosphate will get hydrolyzed better when you have an electron withdrawing group, because the phenolate becomes the leaving group in this case. So, the QSAR on hydrophobicity shows no dependence, right. So, these two data are actually consistent with what we would expect, that A, the insecticidal activity depends on electronics, because the better the conjugate base, the better the leaving group. Number 2, the enzymes that are expressed outside the cell membrane. So, therefore, there is no need for it to get across the cells and get into the cell to exert its activity.